So in our notes today, we're going to review inverse functions from Algebra 2. You have seen these before. So if you're like, Mustapia, you're lying. You've never seen this. Yeah, no, you have. You have seen this before. So with graphs, I'm going to go through all the different pieces of what you learned in Algebra 2 over inverse functions. The first part was with graphs and tables. With a graph or a table, if you create a X and Y chart, what you can do to find the inverse function is switch the X and Y values in your table. So for instance, for this graph that I have, it's the equation f of x equals x plus 2 cubed plus 3. That's this black graph. If I wanted to find the inverse function, there's technically two ways to find it. The first way that you have learned is to pretty much take the points that are on this graph. So I'm bubbling the points that are on this graph that I can clearly see. Take all of those coordinates. And we're going to put them into a table. So for this point here, that's at negative 1, 4. This point's at negative 2, 3. Negative 3, 1. Oh, no, not 1, 2. And then negative 4, negative 5. So I have all of those points. If I want to graph the inverse, all I need to do is switch the x's and y's. So that x and y table that I created, I'm just going to switch the values. So for my inverse, this is going to be another x and y chart. The x's now become the y's. And the y's now become the x's. This is the chart in green for my inverse function for this guy here. This is the equation for my inverse function. So what you guys are going to do is actually plot those points and create that curve. What is that inverse going to look like if you were to graph it? 4, negative 1. 3, negative 2. All the way down to negative 5, negative 4. So your inverse function should look something like this in green. So something like this. So I think I mentioned earlier, there's two ways you can find the inverse function. The most common way is to take the x and y table and literally switch the location of the x's and the y's. The other thing that you could do, which you did learn again back in Algebra 2, is to have it reflect over the line y equals x. Y equals x is the linear parent function. It has a y-intercept of 0 and a slope of 1. So if I ask you to, instead of creating a table, to reflect it over the line y equals x, then you would literally just take your, if you have a ruler, cool. If not, don't worry about it. Just sketch the line y equals x. Doesn't need to be the most beautiful, but should be close. Especially with this graph, I like it because it kind of helps me double check if I did my answers correctly. So for instance, this point here, if I wanted to make sure that this is in fact an inverse or is going to be a point on my inverse graph here in green, what you can do is literally count. You reflected back in geometry, so you should know how to reflect. If you don't, I'm literally going to count how many units it takes to get to the y equals x line. So it takes 1, 2.5 units. I'm going to go keep going, and I should hit the green graph. Half, 1.5, 2.5 units. So you can do that with the line y equals x. I like to see some kind of work just to make sure you guys don't mess this up. So it's up to you. Especially if I don't explicitly state, show me the table. If you just count the units over, that's another way to double check. So that's what you guys did before. And this information down here is also what we've done technically at the beginning of this school year and back in Algebra 2. Okay, so I need to write the inverse for this equation. I don't even have the graph for that equation, so I need to create it. So I need to know first, what is my parent function, Eurydia? What's my parent function for this? Square root of x. So I'm going to make this f of x equals the square root of x. The next thing I need is actual values that will I can actually put on a table. So values that will actually create my square root function. So Itzel, can I use negative numbers underneath the radical? No, I can't. What happens when you put a negative number underneath the square root? What does it become? Begins with the I. Imaginary, yes. So it becomes imaginary. I can't use it. Can I use 0, Itzel? What's the square root of 0? Just 0. So I can use 0. I know I can use positive values, so we can definitely use 1. Itzel, what's another good number to use? Because I can't use 2, because the square root of 2 won't give me a whole number. 4, and will give me one more. 9, there you go. So if I take the square root of each of these, the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Okay, that's my table. I need to take my parent function. Let me write that out. This is your parent function. And I now need to do this transformation, because this is literally just a transformation like we saw a couple weeks ago. So to do the transformation for the x's, I'm going to take this x minus 3 and set it equal to all of your original x values. So I'm going to make x minus 3 equal to 0, all the way down to 9. That's a 3. So once I solve each of those, this is my new x column. If I wanted to get my y values, Valeria, how do I get the y's from this equation, my new y values? That's exactly it. All of this underneath the radical is going to be representative of your y. So all you need to do is take that -2 in front, multiply it, and that will give you part of your new y. Then just subtract the 2 at the end. So right now, you guys compute it. You don't need me. Find the new x's and the new y's. Once you have those points found, graph these out. So take each of those points and plot them. We took all of the original x's and we set them equal to x minus 3, all of the original x's. To find our new y's, take all of the original y's for the parent function and plug it in. So from what I just calculated, I'm going to take each of these points and I'm going to plot them. So we're going to start with 3, -2, 4, -4. For 7, -6, I don't have it, but I want to at least put one more point. And this is just my personal preference. So I'm just going to extend this graph over on the x-axis 7 units so I can go down to -6, which would be about here. Unfortunately, +12, -8, I can't graph that. That's not on this graph. Okay, so that's my function, my f of x. I need to find the inverse. Before I find the inverse of this, let me label the domain and range so that way we at least know what's going on domain and range wise. Valerie S. Valerie S. What's the domain for this pink graph? Go from left to right. What's the domain? Three comma infinity. Beautiful. 3 comma infinity. I know infinity has to have a parentheses, but what about the 3? Bracket. And then Valerie, S again, go ahead and look at the range. Look from the bottom of the graph to the top. Think of Drake. Start at the bottom of the graph and go to the top. Say it again. -2. Negative infinity to -2. So negative infinity to -2. Can I put a bracket again? Yes, that's exactly it. That domain and range is going to help us when we start looking at the inverse. Okay, so all of this in pink is everything for my original function of x. Let's go ahead and find the inverse for f of x. Gabriel, you okay? Okay, I was like, if I need to zoom in, let me know. For the inverse function, I'm going to do f inverse of x, and I'm going to create my table. You could reflect it over y equals x. You could reflect it over y equals x. It is possible. I just also want to give you another option besides just reflecting, because especially with reflecting for some students, it gets kind of confusing. So that's always an option if you want it, but you don't need to. So with the inverse function, I'm going to look at my table. All of the x's become my y's. All of the y's become my x's. So just like I did before, I'm going to graph these out. And I want one more place for +7, so I'm just going to include 7 at the top up here. And I'm going to put the point like right here under 3. That's my inverse function. If you want to double check to make sure you have the right inverse graphed, start with your original and count how many units it goes to your y equals x line, which is your symmetry, or not symmetry, but your reflection line technically. That's what you're reflecting it over. So it's going to go 1, 2.5 units. So I'm going to go half, 1.5, 2.5 to get to my next point, which is technically the same point if I was to reflect it. All right, I need to find the domain and range. Odalis. For my graph in green, what's the domain? Start from the left and go to the right. Beautiful. Now give me the same thing for the range after you finish writing. Start from the bottom of the graph and then go to the top. You're good. Bracket 3 to where? Awesome. That's exactly it. The main reason why I gave you guys a domain and range down here is because I want you guys to think back to the beginning of very top of the page. I literally highlighted switch the x and y values. Domain refers to the x's, range refers to the y's. So all we need to do is when we're looking at the original function of x and we're finding the inverse, the domain now becomes the range, so the x now becomes the y. The range from the original now becomes the domain for the inverse. So literally the x's and y's and the domain and ranges literally change. They're just switched. I just wanted to point that out before we flip over to the back side of the page. So on this back side up here, these two questions, 9 and 10, I'm not going to do. If you choose to do them later, awesome. If not, that's up to you. We're going to look at one-to-one functions. I'm going to have to zoom out for a bit. Okay, one-to-one functions. In order for a function to be one-to-one, it must pass 2 tests. It must pass the vertical line test and the horizontal line test. So right now, take a second and look at all 3 of these graphs. Well, actually just these 2, the 2 that I'm putting a blue check mark, these 2, this graph, this table. Does it pass the vertical line test? Yes or no? Okay, this one definitely does. Does this one as well? It doesn't have a vertical line test. So if you were trying to do the vertical line test for a table, which technically this is not a mapping, this is a table, what are you looking at to see if anything repeats? The x's. Do any of these x's repeat? No. Okay, so both of these pass the vertical line test. I'm going to put pass VLT for vertical line test because I'm a little lazy. And then pass the VLT, which is the vertical line test. Okay, let's focus in on this one here. It also, in order for it to be one-to-one, it must pass the horizontal line test because the question is asking, does the function have an inverse? Okay, well, in order for something to pass the horizontal line test, it cannot have more than one y value for every x value. So what that means is we want to make sure that none of your y values are the same. So we do not want no y values. Clearly forgot to spell values for a second. Values that are the same. We want no y values to be the same. Okay, so horizontal line test, that's side to side. If I was to draw a side-to-side horizontal line right along the x-axis here, it would only touch the graph at one point. So far, it's good. But if I literally go right down the middle of the graph, is this going to pass? Because of these 2 points, it's not going to pass the vertical line test. So I'm going to put a little note, does not pass the horizontal line test. Since it doesn't pass the horizontal line test, that means that the function is not going to be one-to-one, so it's not one-to-one. And there's no inverse. No inverse. So that's what that horizontal line will tell us. It's not one-to-one, which means it's not going to be an inverse. Let's look at the table on the far side, because we looked at the graph. Let's see what a table is going to look like. So for your table, okay, we already said it passes the vertical line test. And I wrote a little note here for horizontal line test. None of your y values should be the same. Do we have any y values that are the same here? Since both of those y values are the same, it can pass the vertical line test, but it's not going to pass the horizontal line test. Since it doesn't pass the horizontal line test, that means that it's not, and I'm going to kind of draw an arrow up here for this, not one-to-one, and there's no inverse. So we've been looking at all these things that aren't one-to-one, that aren't going to be inverse. Let's go ahead and look at ones that will be one-to-one. That means they pass the vertical and the horizontal line test. So down here at the bottom, it says an example of a mapping. I'm actually going to give you a table because honestly, tables and mappings are almost the same thing. Mappings have bubbles to show arrows going from one number to the next. Tables are just tables. I'm going to look at the table for y equals x cubed. That's a one-to-one function. It will pass the vertical line test, which means every x goes to one y, or none of the x values repeat, excuse me. And then it also passes the horizontal line test, which means none of the y values repeat. So for these, if you were to plug in -2 all the way to +2, this would represent a function, a one-to-one function. So if you plug in -2 into this equation and cube it, you're going to get -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1, and 2 cubed is +8. Notice that none of the x's are going to repeat, none of the y's are going to repeat. This is an example of a one-to-one function. On these two graphs, I want you to graph y equals x minus 2 and y equals x squared when x is greater than or equal to 0. These two are one-to-one. Graph this line, very simple. For x squared, when x is greater than or equal to 0, think about how to graph that. We did piecewise functions earlier in the semester. You should be able to graph x squared when x is greater than or equal to 0. For y equals x squared, when x is greater than or equal to 0, I would probably make a table for this. So for the y equals x minus 2, obviously if we draw vertical lines, it'll pass the vertical line test. If we draw horizontal lines, it will pass the horizontal line test as well. For y equals x squared, that's the exact same graph as this, but we're restricting it to only look when x is greater than or equal to 0. So we're really just graphing this right-hand side of your graph. So over here, if you're like, I don't know what that looks like, and I would honestly do this on a test or quiz for your x's and y's, I know that we want all the x's to be greater than or equal to 0. We have an equation. Let's take 0, plug it in. Okay, 0 squared is just 0. I need them to be greater than 0. So let's do 1, 2, and 3 as well. 1 squared is 1, 2 squared is 4, 3 squared is 9. I'm going to plot each of those points. This is the only way to make y equals x squared, which is the quadratic parent function. That's the only way to make it a function, specifically a one-to-one function. When you restrict your domain to only look at really half of the graph, that's the only way. Questions, concerns? All right, we have a couple more to look at. Go ahead and look at the next page. Yes, ma'am. We don't show the table. If I put it explicitly in the directions to make a table, I'll take off points. But if I don't put it in there, no, because I didn't explicitly state it. On tests and quizzes, I don't foresee myself like giving you guys restrictions that you have to graph. I will probably graph them for you. So I haven't figured out how I want to assess you guys on this, but I just want to make sure you guys know that in case you have something like this, it's literally just a piecewise function. Just graph half of it. All right. What is the inverse function? Okay, so we already talked about on the first page, when you have a graph, you can reflect it over the line y equals x, or you can switch the x and y. If you're going to look at an equation, Chelsea, how do you think we're going to find the inverse function for this equation? What do you think we're going to have to do? That's exactly it. Switch the x and y. So on this whole page, I mean, even for tables like we have down here for number 6, you're just going to switch the x's and y's. The most, quote, difficult question that we have here, I think, is 13. So I'm going to go through 13 with you, but then I'm going to move on. The rest of this page is just extra practice for later. So first thing, if you don't remember the steps, you might want to write these out. But the first step, whenever you're finding the inverse, is to replace f of x with the y. That's your first step, to replace f of x with the y. Your second step is to do just like Chelsea suggested. We're going to switch or interchange the x's and y's. So all of these x's become y's. And this y becomes an x. That's the second step. Switch or interchange the x and y's. The third step is to solve for y. So in this problem that we have, I have 2 y's. Okay, think of that as you're trying to solve it. I'm gonna give you a 30-second head start. Your third step in this is to solve for y. So you guys try to solve it. I'll give you a hint. Put this over 1 and cross multiply. That's the easiest way to do it. Put it over 1 and cross multiply. Sign up. One times 2y plus 5 is 2y plus 5. X times all of this is x times 3y minus 4. Remember, in this problem, there's 2 y's. You need to only have 1 when you're solving. So to only make it 1, you have, and if you're like, oh, well, Ms. Toppy, I could just divide both sides by 3y. If you do that, guys, we're back up here where we started. That's not what I want. And you can't subtract it. Let's distribute the x. And now we're going to move 2 things. Ms. Toppy is a little lazy, so she's going to move both at the same time. I'm going to subtract 2y on each side. And I'm also going to add 4x. to each side. So on the left-hand side, I'm going to have 4x plus 5, or you could put it as 5 plus 4x. It's the exact same thing. And it's going to equal 3xy minus 2y. You all should know this from Algebra 1. Melissa, oh, what do I do? How do I make both of these y's become 1? I can't just add these because of that stupid x. Begins with the F. Factor. Guys, that's your favorite word, hopefully soon. This is factor. You want to make sure you factor out one, or pretty much those y's to make it become 1. So 4x plus 5 is going to equal y times 3x minus 2. And then, Melissa, how do I get rid of this 3x minus 2? It's all being multiplied. So what's the opposite? Divide. Divide everything by 3x minus 2. So y is going to equal 4x plus 5 over 3x minus 2. And if you rearrange it to put like 5 plus 4x in the numerator and negative 2 plus 3x in the denominator, it's okay. It'll still get you the right answer. The last thing you need to do before you box this is put this notation, f to the negative 1 power. So if you don't put that inverse notation, I don't know what I'm looking at. So we're going to have 4x plus 5 over 3x minus 2. You have to put that inverse notation. All right, the rest of this page is just extra practice. I have 3 quick questions to look at, and we're going to look at the next 2 pages for it. So let's look at the next page. All right, so with verifying inverses. Okay, so we've talked about how to graph. We've talked about how to prove something's one-to-one. We talked about how to find an inverse. And we also are now going to talk about verifying an inverse. So it's pretty much asking in this question, and for all of these questions, are f and g of x inverses? How do I verify that? We can do that. That'll definitely work. You can definitely do the inverse for this. So find the inverse like we just did on the last page. Find the inverse like we just did on the last page and see if they match up. There's also another way, and it might be a little simple for more people. Alexis? Not quite. Say it again. Almost. The second way you could do this, and you did this in Algebra 2, is to prove that the function composition of f and g equal to x. You need to prove 2 function compositions here. The function composition f composed with g of x equals x, and you also need to prove that g composed with f of x also equals x, or whatever variable I have. So if I put n in this parentheses instead of x, it should equal n, which is just the variable. So if this was an n, this should equal n. So whatever your variable is, that's what it should equal. If you can prove both of these functions equal x, then that means that f of x and g of x are inverses, specifically of each other. Specifically of each other. So that's what we're going to do. We're going to find the function composition for a couple of problems to see if they're going to be inverses of each other. So I'm going to look at example 1 at the top of the page, and then we'll look at 2 more. So for this first question, I'm going to do the function composition, f composed with g of x, which is the same as f of g of x. All right, so we're just doing function composition. We did this a few days ago. I'm going to plug in g of x, which is 2 over x minus 3. I can't simplify anything in there. Now I'm going to take all of this and plug it into the f function. So we're going to make this 2 over x plus 3. Instead of putting in just the normal x, I'm going to substitute 2 over x minus 3. Okay, well, in these parentheses, I always put them there in case you have to multiply something, but I don't here. I don't have to simplify anything. So I'm just going to remove the parentheses and try to simplify. David, what can I do to simplify this? And what happens? It becomes 0. These cancel. So I'm left with 2 over x. David, how do I simplify that? X by 2 or x over 2? Over 2. So I'm going to do the reciprocal. I think I know what you're talking about. This numerator is a whole number. We're going to put that as 2 over 1. We're going to multiply it by this reciprocal, so x over 2. When you multiply that, you technically are multiplying this numerator's 2 with this numerator's x, and then dividing it by 2. You don't have to multiply all of that mess. Just cancel out the 2's, which will leave you with x. So far, it looks like it's going to be an inverse. Try the G one. Try G composed with f of x, which is pretty much the composition that I have right up here. So you guys find it. See if it equals x. After you finish that, you'll thank me because we're going to do numbers 7 and 5. I'm going to do number 7 first, then number 5. So after you finish this part, do numbers 7 and 5. So for the composition, we're going to have G of 2 over x plus 3. Okay, that can't simplify. So I'm going to take this and plug it into the G function. So we're going to have 2 over 2. Try that again. 2 over, I'm going to substitute all of this in, 2 over x plus 3, that looks better, minus 3. If I was thinking of simplifying, which I am, Edgar, can I just cancel these 3's? No, I definitely can't. Thank you for saying no. You cannot cancel these. You have to deal with this ugly division first before you can subtract 3. So you should have keep, change, and flipped this, minus 3. That's a 3. The 2's are going to cancel, which will leave you with x plus 3 minus 3. And x plus 3 minus 3 simplifies to x. So what does that mean for f and g? They're inverses. So f of x and g of x are inverses, specifically of each other. These two functions are inverses of each other. Like I said, we're doing 2 last quick questions on the very last page of this packet, numbers 7 and 5. I'm going to do 7 first, then 5. Let's look at number 7. Number 7 is fun. It's disgusting, let's be honest. So first thing I need to try to find is the composition f of g of x. And if you don't like writing that composition notation, just write it as f of g of x. It means the same thing. I'm just writing it both ways so you guys can get that practice. Okay, so for that composition, we're going to do f of g of x is the fifth root of x cubed plus 10. Yeah, I definitely can't simplify anything in there. Definitely not. So we're going to take this now and substitute it into the f function. So 2 parentheses for x, raise it to the fifth power, minus 10. Some students might find it easier to actually rewrite this as kind of like a skeleton before you plug in numbers. So I have all of this. I'm going to substitute in the fifth root of x cubed plus 10. Look carefully at it. Joseph, what can I simplify in here? Yes, fifth power, fifth root, you can definitely cancel that. These are gone. So I now have cube root of 2. I'm keeping this in parentheses because even though the radical's gone, I can't just put the 2 right next to it because I'm probably going to have to distribute. We're going to have x cubed plus 10 minus 10. Now what? Joseph, what can I do now? Distribute the 2. Notice that he didn't say you can cancel that cube root yet. You can't touch it. 2x cubed plus 20 minus 10. Now what? Okay, so these terms are 10 and 20. I can combine these. So I'll have the cube root of 2x cubed plus 10. Can I cancel those cubes? That cube root and the cube? You're definitely going to say no because that's not what you're supposed to do. You cannot cancel those. The reason why is because this 2 is stuck next to it. This 10 is also stuck next to it. You cannot cancel out that cube root. Anybody else? Can I cancel or simplify anything else in here? I could factor out a 2, but it's not really gonna. That would only really be helpful if I was dividing by something. But I do like your thought process. Yeah, no, we can't factor. We can, but it's not going to change my answer. Unfortunately for us, this is our answer. Does that equal x? No. So what does that mean? They're not inverses. F of x and g of x are not inverses. They're not inverses of each other. Last one I want you guys to start off is number 5. You guys started off. I'm going to give you a minute head start, and then I'll finish it up with you. Question number 5 is like a slap in the face of Algebra 2. It's a lovely one. So number 5 at the top of this page. Counting. Minute. Go. So you're first going to find, we technically need to prove both of these compositions, technically. Let's start with the first one, the function of f composed with g of x, and let's see if that simplifies. F of g of x. Remember, that's the exact same thing as the composition bubble. Okay, so g of x, I'm going to plug that in first. This is 2x over 3x minus 1. Okay, I can't simplify it. We're now going to do f. So we're going to have 8 plus x over 3 times x minus 2. In those parentheses, I'm going to put 2x over 3x minus 1, 2x over 3x minus 1. Okay, Can I multiply this fraction by 3? Yeah, I can multiply that. When you multiply, you're just multiplying the numerator by 3. So we're going to make this 8, I'm putting it over 1 for a reason, plus 2x over 3x minus 1 divided by 6x over 3x minus 1 minus 2 over 1. Like I said, this is a slap in the face with algebra 2. What am I going to do from here? In order to add or subtract, what can I do? Your least common denominator, or find a common denominator here. So just focus in the numerator. I want to say something first. I had somebody last class period just cancel these. Please do not cancel those. You're adding up here and you're subtracting down here. You cannot just cancel them. Okay, so back to the task at hand. I need to find a common denominator for the numerator. Well, that's just going to be 3x minus 1. And then for my denominator, I need to find a common denominator here, which will also be 3x minus 1. It just so happens they're both the same. So up here at the top, I'm going to rewrite my fraction. In the numerator, we're going to have 8 times 3x minus 1. Do we both agree before I write this out? Do we agree that both of these denominators are going to be 3x minus 1? Yes. Okay, let me write one big fraction as 3x minus 1, because we can write this as one big fraction now that they have the same denominator. And then for the rest of my numerator, I'm going to add 2x. So take a second and look at it. Make sure you understand what I just wrote out. You all right? You're fine. For this denominator, I'm now going to rewrite it. Can we agree that these now are going to become one big fraction because of your denominators? Will they both be the same? Yes. Okay, so we're going to have one big fraction, 3x minus 1. The numerator will be 6x minus 2 parentheses 3x minus 1. Once I can simplify these ugly numerators, I can just keep, change, flip from there. So from here, I'm going to distribute the 8, and I'm going to distribute the 2. 8 times 3 is 24x minus 1, or not minus 1, minus 8, plus 2x over 3x minus 1, 6x minus 6x plus 2 over 3x minus 1. Okay, in the numerator, I have to combine my like terms. So we're going to have 24 plus 2 is 26x minus 8. These 6's in the denominator cancel. Right now, I want you guys to keep, change, and flip this fraction. Keep, change, and flip. Can I just cancel everything? Can I cancel anything? What? Oh, this isn't looking nice for just get equal an x. In that numerator, since Jorge reminded me earlier, I can factor out probably a 2 from up here. So that'll give me 13x minus 4 over 2. So these 2's cancel. But I'm still left with 13x minus 4. Is there any way to get rid of that? Just to give me an x? That's my answer. What does that mean? They are inverses? They're not inverses. So up at the top, f of x and g of x are not inverses. If you want a question that will kind of refresh your memory even more of Algebra 2 and test you on like function compositions for inverses, questions 3 and 4 on the other side of the page, so the other side of this page, are going to be inverses, both of them. They will be inverses, but you're going to have some fun stuff that looks just like this. Do y'all have any questions on this before we wrap up? What's up? In order for it to be 1-to-1, yes, it must pass the vertical and horizontal line test. Inverse has to pass the horizontal and vertical line test.